Hello students, welcome to EPG Pathshala. I am Dr. Nilofer from the past Delhi. Today we are going to talk on module voltage clamp and patch clamp techniques. This is from the paper Membrane Biophysics. The objective of the talk are historical background, voltage clamp, its theory, variation of voltage clamp, patch clamp, its principle, patch clamp configurations, its applications and limitations. So coming to the introduction, cells mostly differ in their anatomical, electrophysiological and gene expression properties, signifying unique functional roles for any given cell type. Much of what we know about the properties of ion channels in the membrane of the cell has come from the experiment using voltage clamp. In general, the method allows ion flow across the cell membrane to be measured as electric current, while the membrane voltage is held under experimental control with a feedback amplifier. The method was first developed by Cole in 1949 and then Hodgkin and Huxley 1952 for the use with the squid giant axons. Since then, many variants of the technique have been developed and voltage clamp analysis has been extended to a whole range of tissues. The effectiveness of the voltage clamp stems first from the fact that it allows the separation of membrane ionic and capacitive currents. Secondly, it is much easier to gain information about channel behavior using currents measured from an area of membrane with a uniform controlled voltage. Then, when the voltage is changing freely with time and between different regions of the membrane. This is particularly so as the opening and closing of most ion channels is affected by the cell membrane potential. I want to give you some historical background about the voltage clamp and the patch clamp technique. The excitability of membranes and the cell has always been of major interest for the research on the nervous system. Hodgkin and Huxley revealed the ion channel events of action potentials using voltage clamp technique, and they were honored with the Nobel Prize in Physiology and Medicine in 1963 for their excellent work. During this time, voltage clamp could only be applied to rather big cells as sharp microelectrodes were required to penetrate the cell membrane. In the later 70s, Neher and Sekman advanced the voltage clamp technique and for the first time determined single channel currents across the membrane patch of a frog skeletal muscle. They were also awarded the Nobel Prize in the Physiology and Medicine in 1991. Voltage clamp. The voltage clamp is an electrophysiological technique used by electrophysiologists to measure the ion current through the cell membranes of excitable cells such as cardiac myocytes and neurons while holding membrane voltage at a desired level. A basic voltage clamp will measure the membrane potential or the voltage and then change the voltage to a desired value by adding the necessary current. This clamps the cell membrane at a required constant voltage, allowing the voltage clamp to record what currents are delivered. Because the current applied to the cell must be equal and opposite in charge, the current being going across the cell membrane, the set voltage, the recorded currents indicate how the cell reacts to changes in the membrane potential. The cell membranes of excitable cells contain many various types of ion channels, some of which are voltage gated, meaning open and close in response to change in membrane voltage. Coming to the theory, the basis of voltage clamp may be understood by consideration of the simplified equivalent circuit for the cell membrane given below, where C is the membrane capacity or capacitance, while the currents that allow ionic current is I to flow through the membrane are represented by the variable resistor R, and the current Im flowing through the circuit will be the sum of II and a capacity current. It is very clear from the diagram below. You can see this is showing the simplified equivalent circuit for the cell membrane in figure A. In figure B, typical currents recorded from a voltage clamp excitable cells when the membrane potential is stepped in a square manner to a level at which voltage gated ion channel open. Spikes of capacity current arise at the edge of the pulse. During the pulse, inward and then outward ionic current flows. The time scale is typically in the order of milliseconds. Variations of voltage clamp techniques. A variety of different voltage clamp methods can be used to study the properties of the membrane. The choice of method depends mostly on size and the shape of the preparation to be studied. I mean, preparation means different type of cells to be studied. The first one is axial wire method. Axial wire technique is applicable to long cylindrical cells such as giant axons of squid and barnacle giant muscle fibers. This method is limited to the cells of diameters large enough to permit penetration of axial wire without damaging the membrane properties. The next one is gap method. Gap method are also appropriate to elongated cells, though their diameter does not have to be as big as it does for axial wires. For example, myelinated axons and vertebrate muscle fibers. The third one is suction pipette method. Suction pipette methods have been used with preparation that can be dissociated to give isolated cells. For example, cardiac myocytes or neurons. The whole cell configuration of the patch clamp technique uses a pipette with a smaller tip, usually 1 micron, and can be applied to many types of cells which are too small for other voltage clamp methods. The next one is 2-electrode voltage clamp using microelectrodes. The 2-electrode voltage clamp technique is used to examine properties of ion channels. Experimenters use this technique largely to study membrane proteins expressed in xenopus oocytes. Dual cell voltage clamp. The dual cell voltage clamp technique is a specialized variation of the 2-electrode voltage clamp and is only used in the study of gap junction channels. Next is single electrode voltage clamp. Single electrode voltage clamp illustrates a set of methods in which one electrode or pipette is pressed onto the cell. This single electrode carries out both functions, current injection and recording. For example, the patch clamp technique. Patch clamp technique. There are two methods by which patch clamp technique can be applied. One is conventional patch clamp technique and the second one is high throughput patch clamp systems. The first one is conventional patch clamp technique. In this, patch pipettes are used and different configurations can be used. For high throughput patch clamp systems, mainly automated patch clamp systems are used. The patch clamp technique is tremendously powerful and flexible method for studying electrophysiological properties of biological membrane. It allows the recording of macroscopic whole cell or microscopic single cell or single channel currents flowing across the cell membrane. So before performing the patch clamp technique or patch clamp experiment, we need lot of equipment or we need a patch clamp setup. For this setup, first of all, the vibration free or vibration isolation table is required, inverted microscope, micromanipulators, patch clamp amplifiers, analog to digital converter, oscilloscope, pipe fabrication. For that, we need micro pipette pullers, we need coaters for hydrophobic coatings, microelectrodes, chambers and computers. These are the requirements to perform patch clamp recording, or these should be there in patch clamp setup. The principle of patch clamp. A glass pipette with a very tiny opening containing electrolyte solution is firmly sealed onto the neuronal membrane or any other cell membrane and thus isolates the membrane patch electrically. After the application of a small amount of suction or gentle suction to the back of the pipette, the seal between pipettes and the membrane becomes so tight that no ions can flow between the pipette and the membrane. Thus, all the ions that flow when a single ion channel opens must flow into the pipette. The resulting electrical current, though small, can be measured with an ultra-sensitive electronic amplifier connected to the pipette. Recording this current allows conclusions about the membrane conductance. This is the figure. It is showing the general principle of patch clamp recording. In this you can see at the cell membrane a patch pipette having a single channel and amplifier and the recording electrode. Patch pipette. Patch pipette are the most important part of any recording. These can be made by carefully heating and pulling a small glass or a quartz capillary tube. A very fine pipette tip or pipette can be formed. When pulled by a machine or pipette puller, the tip will be much smaller than a human hair and the opening on the end of the pipette may be only 1 micron in diameter. The tip of the pipette can be fire polished meaning making smooth with the help of a microforge. Patch electrode fabrication or patch pipette fabrication. For any patch clamp experiment, several steps are essential to make a proper glass pipette, because if the glass pipette is made easy or nice, then only you can get a nice recording. For that, a glass that has optimal properties is selected, and the properties of the glass differ substantially for single channel recording and whole cell current measurement, which I am going to talk about later. For single channel measurements, low noise is the most important electrical parameters, whereas for whole cell recording, dynamic performance is the most important than the contribution of the electrode to the background noise. Electrodes pulling or electrodes making. This can be done on any commercially available electrode puller. Modern computerized pipette pullers are capable of pulling glass with almost any thermal properties into the proper blunt tipped shape that is ideal for whole cell recording. Therefore, almost any glass can be used to form whole cell pipettes. The next important part is coating of pipettes. The coating of pipettes with elastomer reduces electrode noise in single channel recording. In whole cell recordings, the noise related with electrode glass is usually insignificant in comparison to other noise sources, and so elastomer coating is not often required for noise reduction. Elastomer coating also reduces pipette capacitance. The next part is fire polishing of the pipette. To enhance gigaohm seal formation and to reduce the chance of tip penetration into the cell during seal formation, electrode tips should be fire polished. Sealing is generally prompted by fire polishing the pipette tip, particularly for the cells where seal formation is difficult. General properties of pipette glass. Various general properties of glasses must be taken into account when trying to make best possible pipettes for patch clamping. The first one is thermal property. Thermal property decides the ease with which desired tip shapes can be formed and then determine how easily the tip can be heat polished. The next one is optical properties. Optical properties frequently result in a distinct visual endpoint so that tips can be fire polished with the same way each time. Next is electrical properties. These properties are significant determinants of the noise of the glass generates in a recording condition and determine the size and the number of components in the capacity transient following a change of potential across the pipette wall. Glasses are complex material made of various compounds, and most of their properties are determined to a first order by the composition of the glass used. Now coming to the patch clamp recording. Marvelous technical breakthrough that improve the signal to noise ratio of the recording. Record from whole cells or from the small patch of cell membrane, so only a few channels or even a single channel can be studied. High resistance or gigaohm seal and high mechanical strength of the seal between the glass electrode or patch pipette and the cell membrane enables one to observe very small currents even at picoampere scale. And the diameter of the tip of the patch electrode can be larger than that of a fine-tipped intracellular microelectrodes. It varies from 1 micron versus 0.05 microns, so that the resistance of the patch electrode is lower. For example, 5 megaohm versus 200 megaohms. The lower resistance of patch electrodes make voltage clamping easier. Patch clamp basic circuit. The glass is fire polished, so there are no jagged edges. The pipette is backfilled with an ionic solution. Normally, it's a 3 molar KCl solution. When applied to the membrane, a small suction pulls the membrane into the pipette with one or more channels. This results in the resistance of over a gigaohm seal or gigaohms. The giga seal of the membrane pipette connection is both electrically tight and mechanically tight. In this figure, you can see the cell and the patch clamp pipettes, bath electrodes, and the other component of the system. Now coming to the patch clamp recording configuration, there are various patch clamp configuration. It can be attached patched, whole cell recording, inside out patch. These are also called excise patches and giant patches, outside out patch. Each of the 4 different patch clamp configurations has properties that are useful for studying different kinds of problems. Recording from cell-attached patches imposes very little perturbation on the cell under study. It allows single-channel currents. Nearly all of known types of ionic channels can be resolved. Whole cell recordings are routinely used to study electrical currents carried by ions through ion channels, neurotransmitter receptors, and electrogenic transporter in cell types of virtually any type. The cell-free configurations inside out and outside out have similar high current resolution and provide control over the ionic milieu on both sides of the membrane. Advantages of patch clamp configuration. Each configuration has its own advantage, like cell attached or on cell patch. It is type of single channel recording. In this, cytosolic side is intact, or this is more kind of physiological recording. In second one is outside out patch. This is also can be done in single channel recording. In this type of recording, extracellular side can be perfused and cytosolic environment is controlled. Third one is inside out patch. In this, single channel recording can be performed and cytosolic site can be superfused and extracellular environment is controlled. In whole cell recording, macro current recording can be done. Quick accession of ion channels, cytosolic environment is controlled and extracellular site can be superfused. Perforated patch, macro current recording can be done. No washout of organic factors, cytosolic environment is controlled and extracellular site can be superfused. Variations of patch clamp technique. The whole cell is the most popular configuration of patch clamp technique. It is easy to obtain among all and it allows the use of intracellular and extracellular recording solutions, particularly devised to isolate the ionic membrane conductance of interest or to intracellularly applied modulators or drugs. In this figure, you can see how the whole cell this configuration can be achieved or different outside out patch configuration can be obtained. This diagram is showing cell attached or on cell patch configuration, and the next one is showing the whole cell patch configuration, and the third one is showing inside out patch configuration. Outside out patch configuration, this is the most difficult configuration of the patch clamp technique. In this technique, for to get outside out patch, the membrane or to be sealed tightly, fine tip or the glass tip approach to the cell membrane and applying gentle section, the gigaohm seal can be formed. After getting giga seal, the whole cell configuration can be obtained by breaking the cell membrane in the patch pipette. After getting the whole cell, the patch pipette, it pulled slowly and the piece of membrane is broken. When it's out, the membrane seals and you can get the outside out patch configuration. It's showing the gating of ion channels. Gating is nothing but opening and closing of channels. So this diagram is showing a patch clamp recording of current reveals transition between two conductance state of a single channel, closed and open. First one is the topmost is the closed state is showing, and the lower side or the bottom side it is showing the open state of the channel. Automated voltage clamp technique. Cell membranes, receptors and ion channels are among the most significant drug targets, and direct electrophysiological measurements. Ionic current is method of choice for analyzing the effect of potential drugs on ion channels and transmembrane receptors. Therefore, a number of automated techniques have been used using either pipettes or planar substrates to automate patch clamp recording from cultured cells that heterogeneously express a target ion channel. Automated electrophysiological assays are of great importance for modern drug discovery, and a variety of approaches have been developed into practical devices. Now, applications of the patch clamp or voltage clamp. The patch clamp technique can be used to great effect to help determine the mechanism of action of a compound. This technique is still the gold standard for studying interactions of drug molecules and ion channel receptors or ion channel itself. Patch experiments can provide comprehensive characterization of drug effect on ion channel function more reliably than any other indirect method. Despite its low throughput recording, the number of compounds tested, patch clamp is considered as inevitable in drug discovery. The great advantage of patch clamp in cellular physiology is that it allows sensitive and reliable analysis of electrical activity of cell membranes at the molecular level. The patch clamp recording is the primary tool for studying structure and function of ion channels. It is among the few techniques that allows protein to be detected at the single molecule level, and the measurement contains much information on the heterogeneity of channel conformations and their dynamic properties. Limitations of this technique. The application of voltage clamp technique to membrane patches and whole cells has allowed the high resolution electrophysiological characterization of biological membranes and the properties of ion channels that exist in these membranes. Despite its widespread application and continuous improvements, voltage clamp or patch clamp remains a challenging methodology to many researchers because of the requirement to operate fairly sophisticated electronic instrument in labor intensive and low throughput operation. So, students, let us now summarize what we have learned in this module. The voltage clamp technique is the gold standard for measuring the function of ion channels, and the patch clamp technique has allowed the currents through single ionic channel to be studied from a wide variety of cells. The whole cell recordings are routinely used in the electrophysiology laboratories to study electrical current carried by ion through ion channels, neurotransmitter receptors, and electrogenic transporters in cell types of almost any origin. and the susceptibility of the channel to various compounds that may block the pore or otherwise influence channel properties. Since the introduction of patch clamp technique in 1981 and the subsequent development of commercial amplifier, this method of intercellular recording has basically replaced sharp electrode recording, mainly in the study of cultured cells.